Hey everybody, welcome to Cassandra Lunch 21. What started as a COVID edition of a meetup group that we've had in Cassandra and in DC is basically it's a web series. It's a live meetup that you guys can, that you all that are here, you guys can join, or you can watch this on YouTube as well. And soon, not today, we're going to start using YouTube Live to stream this out. Today we're going to be talking about Cassandra thread pools. We've been talking about a lot of different topics related to Cassandra. The goal of this series is, either somebody volunteers to talk about a topic, or I'm just going through all the different Cassandra concepts one by one, giving my understanding and pointing people to resources. And at the end of every session we recorded, we write up a blog post and we put that on our blog. The team that organizes this is myself and Akwi. Akwi is very much involved behind the scenes to make sure the content gets out there, it's recorded, it's published. So I want to thank Akwi for all your hard work. You've made this last quarter, and actually we started this, I guess, the quarter before, but we've been recording primarily this quarter. So great work in helping us get this content out there. So thank you, Akwi, appreciate that. If you want to help co-organize, love to have you. In fact, with Cassandra, there's a lot of personalities that we can bring to come and talk about different aspects of Cassandra or technologies that work with Cassandra. I know plenty of people from Datastax as well. I've been personally hesitant in inviting people until we get a critical mass of basically content and also a basic group of people that are coming back before I invite some heavy hitters. We are actually a part of, this meetup is a part of a larger data community in DC. This is a nonprofit that is very inclusive, and we actually are made up of 8. So including this meetup, there's 9 different meetups in this, and there may be even more. There are always new groups that come into this fold. We cover Cassandra and Cassandra variants and things that talk to Cassandra and Cassandra variants. So we'll talk about Spark, we'll talk about Kafka, we'll talk about Kubernetes, we'll talk about Datastax, Cassandra, Yugabyte, Cosmos, managed key spaces, Astra, you name it. Normally this time, if there's somebody new to the team being this group, new to the group, that hasn't introduced themselves, you're welcome to show your face or not, and just say hi, and why you are here and what you want to learn about Cassandra, or if you can contribute something, we'd love to hear about that. So I see a couple of people. So Sunita, do you want to just say hi and tell us about yourself and what you're trying to learn about Cassandra?
Hi, Rahul. This is Naran here. I think it is Sunita's iPhone. I've just been following some of the series on the Cassandra, right from the series being conducted from Datastax, trying to get into more depth of what Cassandra can offer as a skill database. I'm trying to attend as many seminars as I can so that I can gain knowledge on the database and start doing some of the projects. At this moment, I'm doing some POCs, but trying to get into real-time implementation.
Great. Yeah. Well, welcome, and if you want any help with something, there's definitely the Cassandra Apache Cassandra Slack the Apache Slack, where there's some Cassandra Slack teams, but we also have a Slack team that if you want to join, just talk, welcome. We'd love to help you do whatever you need to do. Always a fan of people getting into Cassandra, and I want to give them all the resources possible. So great, good to hear from you. Chuba, do you want to say hi and just introduce yourself a little bit? It's you're muted if you're speaking. I can ask you to unmute. I'll give you about 5 seconds, and then I guess if you don't want to, that's okay. All right, we'll continue. Group rules, if you have a question, just ask it, be polite and be courteous to others, share what you know. So, it's a community, so just step in and with Zoom at least, if you want to be more polite, you can just raise your hand or put a question in the chat. That also works. Datastax is a sponsor and a partner. So is GW University, George Washington University. They give us space in DC when we were having in-person meetups. And then also we have some more local sponsors, Wavical in Chicago, Eastern Foundry in the DC area. Organizationally, Data Community DC is supported by a lot of folks such as American University, Capital One, Data Society, you name it. So we're really fortunate to have this type of backing. Any announcements? Somebody looking for a job, somebody hiring, if there's any hackathon events, etc. We actually have a couple of announcements ourselves. Okay. Cassandra Lunch is all available on YouTube. Just go to Google and look for Cassandra Lunch, or go to YouTube and look for Cassandra Lunch. Cassandra.Link is a site that we publish daily at like 4 o'clock in the morning. It starts generating the site. It's got a couple features that recently pushed out, which is a directory of Cassandra use cases from different companies that's still getting flushed out. There's also a job section where we aggregate just Cassandra-related jobs. And the Cassandra Toolkit is a starting point for anybody that's using Apache Cassandra that doesn't have a commercial distribution, like let's say Datastax. It's just a guide, how to get metrics set up, how to get logging set up. There's some tools that we've also made to do some offline, which is really in a related project. Some events, normally there's some events, I don't think there are any coming up from our end at Anant, but we are actually partnering with Datastax to do an event on October 6th, which is next week. It'll probably overlap with this, so we may replace the Cassandra Lunch with that particular meetup information. But it's a workshop on building a real-time event-driven API with Kafka and Cassandra. This is a follow-up to the workshop we did with Datastax about how to quickly make an API with Astra using Node and Python. So this one, we extend that work using Kafka and Kafka streams, and essentially show people to expand a regular API and how to make that API event-driven. So really excited about that. And that's it in terms of the announcements. We can go ahead and start talking about what we came to talk about, which is Cassandra. Today, as I mentioned, we're going to cover Cassandra stages or Cassandra thread pools. We talked a little bit about last week thread pools and how they help with managing the read and write path for Cassandra. The write path being how the data gets in there and gets replicated and gets stored properly, and eventually it makes its way to the SS tables, how the data is updated, how data is maintained, and then finally how the data is read. Now, this is what Cassandra does. It's a database. Databases store data and they retrieve data for us. But how does it? How is the system engineered? Well, it's engineered as a set of I liken it to a set of microservices that move messages around. Cassandra's architecture on a node basis, on a given node, is that it's actually running these different threads, which is roughly, 20 different threads. And these threads, if you open up the log file for, system log, which is the main Cassandra system log, you'll see log messages from all of these different threads. So Cassandra is written in Java, JVM, and the JVM has the ability to do multiple threads at the same time. What each node does is it keeps several different threads for each of these processes, and it passes messages around. And we'll talk about each of these in a minute. But these messages are you can see the statistics of the messages using a tool called nodetool tpstats. But the threads are essentially taking messages, and they are either, there's a queue where the messages are waiting, they're pending as a task to be executed. They're active, meaning some sort of task is being executed actively for that thread. They could be blocked for whatever reason, probably over here, meaning it's not able to run for whatever reason. It's completed when it's done, and then finally, sometimes it can't do it, so it basically drops. After a while, it gets blocked, it gets dropped. So if you think about it, 20 different threads times 5 different stages, essentially at any given moment, there are 100 statistics that are being stored in Cassandra's JMX, and in the new version of Cassandra, it will be available as a virtual table. But you can always understand the health of Cassandra, one node, by seeing the status of these threads. Now, all these threads are not created equal, because some threads are needed more than others. Some threads are needed in certain circumstances versus others are not. So for example, when data is coming in, and we talked about this last time, and is getting written and read, the following will probably be more busy because it deals with writing data. When data comes in, it goes to the commit log, and then it goes to the mem table. And then every now and then, from the mem table goes to SS tables. And once it's in the SS table, it gets compacted. And then once it's compacted, later on, when somebody comes to read that information, we have some read stages. And sometimes when the data comes and gets updated, we have a mutation stage. So while that's happening, some of the other threads are not going to be prioritized, such as anti-entropy, which is a repair task that generally happens when we say to the system, go and repair this information. Or the cache cleanup executor, it's not going to happen all the time. It generally happens later when the system is freed up with resources. But the more you understand what each of these threads does, the better you are at understanding the sequence of events. And what I mean by that is this is not a monolithic system. It's a multi-threaded system. It's got a bunch of different things happening. And as I said, I think I've said earlier, these are like microservices. They're basically running, these microservices are running to empower the database to serve up data at scale. And so each table is kind of like a service that is being helped by all of these different microservices. And because they're so highly, they're so distributed, as we keep adding nodes to the cluster, these threads continue to scale over time. Okay, I'm going to bring up a visual to make it a little bit easier to understand what I mean by threads. This is probably one of the better explanations I've seen. It's an old article, and generally, even if the internal engine changes, these threads are not changing. The queues are not just generally changing. But let's say a system outside of Cassandra asks for some information. Well, it goes to node 1. And node 1 may recognize that it doesn't have the data that it needs, so it acts as a coordinator. It then takes that and it sends a message to node 2 to to say, hey, I need this information. And while this is happening, it may be doing a bunch of other things. It may be responding to other requests from other nodes as well, but it's going to do it basically depending on how much memory and CPU is available to it. Eventually, it's going to give that message back to node 1 to say, I've got a response for you. And then the client will get their data back, but it may send another message to say, hey, let's do a read repair, because this was a consistency all read, or this was in the 1% of the time or the 10% of the time that we do a read repair, okay? And you can visualize, this is an older version, right? This is written in 2014, so some of the names of the threads have changed. But basically, you're seeing what I was showing you earlier. You have these different stages. Some are active, pending, completed, blocked, and then all-time blocked is a slightly different one. I think there's a new stage as well, which I mentioned, right? So we have pending, blocked, active, completed, and dropped. So dropped, you don't see it on this one because this is an older statistics dump. This data, all of this data for these threads are available via JMX. JMX stands for Java Management Extensions. And, if we want to know what's happening, you can talk to JMX and get it. Obviously, you're not going to do that. If you have 100 servers, you're not going to go to the JMX shell and say, hey, what's this metric for me? What you're really trying to do is to get that information and put it somewhere so you can review it. A lot of times, you can take this data and put it into Prometheus, right? So the Cassandra exporter, or Prometheus. And there's a couple of different implementations of it. But basically takes all that information and more, right? Not just tpstats, and it puts it into the Prometheus database. And if you want to take a look at that data over time, right? What does that look like over time? That you can visualize it with Grafana. So that's one way to look at this information. The other way is with something called Ops Center, which is a part of Datastax, which automatically does this, and it stores the data in its own Cassandra database, and it helps you visualize this information. The data is also available via something called Ops Center API. But with Cassandra 4.0, since this data is all going to be virtually available using these things called virtual tables, you'll be able to look at this information via a CQL query. And if you can see it via a CQL query, it'll be much easier to take it out of CQL and put it into, let's say, Prometheus, or even just do a direct live view of what's happening, right? And if you want to do an in-depth review of how to really measure this stuff, I would say there's a lot of resources. There's a blog post that I'm gonna actually link in the chat, as well as eventually it'll go to the blog post that we're about to post for this session. And I actually mentioned several different tools you can use for Cassandra and Spark, but as I mentioned, there's lots of guides on using Prometheus and Cassandra, or let's say Grafana and InfluxDB with Cassandra, and that's not the end of it. The threads inside Cassandra are not the only thing that we need to take a look at. There are other statistics related to the tables, and we'll get into table statistics at another time. That's called table stats. Today we're focusing on tpstats. So what happens in Cassandra when it's running is that if the system is busy, it's going to try to direct some of that load to other nodes. Meaning if your driver code is configured properly, it'll sense that a machine is busy because all the threads are basically blocked, right? They're too active. It's not able to take anything else. So it basically tells the client, look, I'm busy. So if the driver is configured properly, you'll go to another node. Now, that being said, if you don't know how these nodes are performing on one node, and especially in a cluster, how they're performing in conjunction with the other nodes, you're not going to know why is this node busy. You know, the reality of a distributed system is that these threads should be distributed as evenly as possible across the different members of the cluster, and no one node should be doing more compactions than, let's say, another node. No one node should be doing more memtable flushes than another node. So, right, we talked about 20 different stages, and there are other statistics. So, for example, compaction has other statistics like how many bytes were compacted, right? Those things are also available via JMX, but just the number of threads and the number of items or tasks that are being processed by the threads, just that information alone. So we have 20 threads, we have, you know, potentially 5 different states, 100. Imagine if you had 10 computers, 10 cluster members. That's 1,000 data points every time you collect. But it's important. Even if you get every 5 minutes what the stage is, what the state is of the system, okay? Where's that blog post I just showed? Yeah, here we go. You know, if you have every 5 minutes, this is a snapshot in time, right? So if you have every 5 minutes a snapshot of this information, you can then start to see trends that this one particular node is continuing to increase in pending, right? Compaction pending keeps increasing, and it doesn't go down. Why is that? Or the read repair stage is not really happening on this one node, but it's happening on all of these other 9 nodes. Why is that happening? So the knowledge of the threads, what they do, the knowledge of the states in terms of the statistics on one node, and then obviously the rest of the cluster, visualizing that data is what allows a Cassandra expert to understand why Cassandra is not performing the way it should, which is fast. It's supposed to be fast for everybody all the time. All the nodes are supposed to be fast. So there are updated versions of this stats. So let's take a look at that. And I believe the one I have here is from the Datastax documentation. Right, so this is basically the most updated version of that. Looks like mine was the drop. The drop doesn't show here, but it is being counted. It is being counted elsewhere, and it's actually right here. And I mistakenly told you that it's going to be next to this, but you do get certain tasks statistics from the same place, but they're being stored in a different metric. But yeah, so back to this. So when we're taking a look at this, and we see that a system is not being performant, the first thing that we're going to ask is, are they all not being performant, meaning all the cluster members, or are only some of them not being performant? So how would we know if a Cassandra cluster is being performant or not? Well, it would be because, let's say you had one node and it did so many transactions, and you added 2 more nodes and it didn't scale linearly. That would be one signal. Even without caring about each machine, if you have one node cluster and you add 2 more nodes and it didn't scale linearly, and it probably wouldn't because, you know, we still have a replication factor of 3. But let's say we had 3 nodes and we went from 3 to 6. You would expect the performance to double. So if you went from 6 to 12, you would expect the performance to double. And if it doesn't double, then we have to ask ourselves, like, what is happening in each of these machines? Are any of these threads bottlenecked? Because, quite frankly, this is Cassandra. This is the whole operating system of Cassandra, are these threads. If these threads aren't healthy, then that's the reason why the system, that particular node, is not healthy. So I'm going to pause for a second before I go further into each of these. But any questions so far? Check the chat here. All right. So, you know, if you this link will also be put there, but the same article, the Guide to Cassandra Stages, that I showed earlier is what is linked from the Datastax documentation page. It actually tells you on each of them what this is, how to configure, how to tune it. So you're not just, you know, aware of what the thing is, but like how can, if it is being blocked, how can I tune it so it's no longer blocked? Okay, and not everything is tunable from a configuration standpoint. Sometimes it's a data model issue, and you can't really tune the system. And I would say 80% of the time it's a data model issue, well before it's a Cassandra tuning issue. So let's walk through this, and so that you get a high-level understanding of what these things are, and you know, the more you understand about these threads, the more intelligently you're going to be able to diagnose issues when looking at a log, right? As I mentioned before, the log, system log, is actually telling you what each of these things are doing and what the errors are, what the warnings are. We will do another in-depth on statistics and troubleshooting, where we will come back and refer to this, and we'll take a look at a log file and we'll walk through to see what's happening. Anti-entropy basically is essentially repair. Repair is a bad word. It's synchronization. It synchronizes the different replicas that are in the system, and it synchronizes it because entropy is a part of distributed systems. Entropy meaning chaos. Sometimes data does not sync, so we go back and make sure that it does. Also used, you know, streaming. What streaming means, like when a node is, a new node comes up and it doesn't have data, anti-entropy has a part to do with making it stream that data from one node to the other. Cache cleanup. There are different caches in Cassandra. Row cache, key cache, bloom filter, off heap cache. I mean, there's so many different places. The mem table itself is in memory, but in some sort of cache. So even though Java is going to do its own garbage collection of the heap, internally Cassandra tries to clean up its cache every now and then, especially stuff that's not being used. And when it does that, it actually updates some statistics related to something called the key cache hit ratio. And if you have a cache and you're not using it, it's basically useless. So this is useful. Commit log archiver. So when you know, you want to do something called like incremental backup, essentially the best way to make sure you can always get to a certain point in time from Cassandra is to have copies of the commit log. If you just take commit logs from like one server, well, I have to test that. But let's just say you have backups of the commit log directory. The system just goes down, it's lost. But you know you have the commit log. Even if like you were able to stream all the data in the SS tables from other nodes, you will not have potentially the commit log. So the commit log, if you have it, it will replay those messages. So commit log archiver helps you copy it without, you know, basically interfering with the system. Compaction executor. This is very important. This is what we talked about last time, is that once the data is in an SS table, and it's in an SS table because it keeps appending new files. If you're familiar with Solr, Solr has indexes and then eventually merges the indexes. Compaction is like merging. It's almost exactly the same. It just merges the files so it's more optimal, right? Just like in Solr, if you're going to read an index, even if you have a bunch of it in memory, you don't want to have to replenish that index from 50 different files. You want to have merged indexes. But the compaction of an SS table is much more resource intensive because we're talking, as we had talked about before, we went over the SS table structure. There's a lot of things that are happening in compaction. It's merging partitions, it's removing tombstones, evicting tombstones, and it's quite a busy operation. Counter mutation stage. So counters are a type of data that normally, unless you need it, you're really not using it. Essentially, I would not recommend using a counter. It's not a idempotent data. It doesn't act the same way as other data points. You can't put indexes on it. There's a bunch of different reasons. So, but when a counter is updated, it is updated differently than when a regular, when a normal data key value is updated. Gossip stage. Gossip is the mechanism in which different nodes talk to each other to let them know about the state, the health of the cluster, as well as how to keep itself in sync. Gossip is not how data is streamed. Gossip is not how, when you do a read of data, that is not how gossip doesn't do that. Gossip is very lightweight. It literally tells people, hey, by the way, I'm up and running, right? And it does it in a decentralized way. It broadcasts and everybody figures out, depending on which snitch you use, if you're using a gossiping property file snitch, the snitches, each of the nodes basically self-discover each other and say, oh, I'm in this cluster, I'm in this rack, I'm in this data center. Gossip tells each of the systems the state of the schema. So, what do we mean by schema? Well, each node of the cluster has a sense of what the schema is, right? That's meaning what the data structure is. How else is it going to keep all this stuff together? Sometimes, and a gossip generation means that how many heartbeats of the system are we at? So if one system is way off course than another gossip generation, like one gossip generation may be 5, and another one is like 27, it's going to be like, wait a second, you don't really know what's going on here. You don't really understand the schema as it exists for everybody else. You need to update yourself. That's the kind of stuff that gossip does. It doesn't move data. That's not what it's for, okay? Hinted handoff. Hinted handoff is what, basically, let's say a node is unavailable. Another node will take the mutation, not a read because it's not available. It's just any changes to the data. It will take it and it will store a message. It used to store this information in Cassandra tables. But what we found was that if a node is down and a Cassandra table is storing all these mutations and a bunch of data is coming in, then the Cassandra table that is storing the messages starts to get busy, and then it starts to create compaction. So it was like a vicious cycle. So recently, the hints are actually stored on disk. It's like a commit log, but it's not a commit log. It's just stuff that didn't get sent to other nodes. So, when you see a bunch of hinted handoffs, that means some other node is not up and running. And sometimes we need to disable hinted handoff because we know we're going to have 2 or 3 machines down for maintenance. So we just turn it off because we know that it's going to be down for maintenance. Internal response stage. So this is inside Cassandra, meaning not other systems talking to Cassandra, inside Cassandra. It's for non-client initiated messages, including bootstrapping and schema checking. This is the type of thing that moves data, okay? This is the type of thing that moves data. Gossip stage does not move data. It just sends state information back and forth. Memtable flush writer. Memtable is where data comes in. When you write data to Cassandra, the reason it's able to give it back to you quickly is because it stores it in the commit log, it puts it into memtable, which is a Java object, even before it goes to disk. But eventually, when the memory fills up, that memtable has to be flushed into SS tables. So when that's happening, the commit log is cleaned out, memtable is then put into SS tables, and a busy memtable flushing writer means that a bunch of data is coming in. Right? There's a bunch of data coming in, so there's the memtable flush writer is busier. Right? Memtable post flush. Memtable post flush means that after I have saved everything to the SS table, I'm going to clean out the commit logs, right? And clean out any secondary indexes or update any secondary indexes as needed. Memtable reclaim memory. I've flushed my memtable. I've cleaned up after myself. I need to get that memory back. So it's no surprise that memtables take up 3 out of the 20 threads, because memtable is the reason why Cassandra is so effing fast. It is literally the reason why it's different from, let's say, like HBase, because you put data in and you immediately can get it back. So even if you didn't have any of the data on disk, you'd still be able to operate as if you had a cluster. Migration stage. This is what moves schema changes. Whenever we do a schema change, we tell the system consistency serial, or consistency all, but consistency serial is better. And we say alter table or alter key space. That change is it's called a migration stage task, and it then gets propagated across all the members of the cluster, because each change to this each change to the schema is actually an update to Cassandra. Cassandra runs Cassandra on Cassandra. Cassandra runs basically itself on Cassandra tables, system tables, schema tables, etc. Right? To make a change to the schema means to make a change to other Cassandra tables. Well, this is what is responsible for those changes. Miscellaneous has a bunch of stuff in there. Replication data after a node has been removed, meaning like machine is down, you're not going to replace it. Miscellaneous will try to replicate the data from one. It'll replicate the data from the other two replicas to another node. Snapshotting is basically backing up data. We'll talk about backup restore at another point. We have talked about it, but we'll talk about it again. Mutation stage. This is what is responsible for changing data. Insert updates, schema merges, commit log replays, or hints in progress. Everything that is a change in data comes down to this mutation stage. There's a note here, high number of pending write requests indicates the node is having a problem handling them, meaning you can add new hardware, or you can tune the hardware, or updating the data models. Notice they come down to data models. So this pending, technically every single thing here could have a pending that gets really out of whack, okay? So you always want to see, what is my state, right? Do I have a bunch of stuff that is pending? Why is it high? Okay, so mutation, transport, native transport requests. This is when the system is processing CQL. Cassandra doesn't talk to Cassandra using CQL. Cassandra talks to the outside world using CQL. So when you see this native transport, that means that from the outside of the cluster, somebody's trying to talk to Cassandra via CQL. So what does it mean? It means that, let's say you have 10 servers, and one server has more active native transport requests than the other ones. That means that something is off. That means your driver configuration is off. It's not talking to the whole cluster. So native transport request tells you traffic coming from the outside world. And you want this traffic to be even across the cluster. You want all these things to be even across the cluster, but you can control this. Even if you don't know what was going on outside of this, you could control how your data gets spread around the cluster. One of the big things is that if your data model isn't good, if you have bad key design, you will end up having more native transport requests on some nodes than others. Classic case of hotspotting or data skew. And data skew ends up being traffic skew. Pending range calculator, basically there are, whenever you remove or you add a node, you need to figure out what are the ranges that need to be basically, moved, right? Anyways, it does that work. And apparently the statistics available for this aren't any good, but that's what's happening. The code here is more important than the statistic. Read repair stage. Read repair is different than what anti-entropy is doing, which is nodetool repair. Technically, it does the same thing, but a read repair is doing a repair on data based on some sort of percentage. So normally, like if you say read repair chance, that's a global one. There's also called DC local read repair chance. These days, you don't set a global one unless you know what you're doing. But what a read repair does is that based on this percentage, if I have let's say 100 reads, 11% of the time, it will try to synchronize the data for me. Okay. If this becomes high, if the pending grows to large, we need to reduce this because it's essentially something that we may want to do elsewhere using something like nodetool repair, or in Datastax there's something called node sync. We don't want read repair to do the work. If you set this to 100%, it's going to make everything consistent all the time, but it's going to be very expensive. It's going to be very busy, and you might as well be at that point thinking about using a regular relational database. Read stage. This is what does a local read. Local read meaning the client connection does not talk to read stage. The client connection talks to this, which then sends a message to this. Well, technically it sends it to this, but and then this sends it here. Read stage is what gets the data. If you have a lot of read stages pending, okay, it's going to lower your, it's going to increase your read latency, which means it's slow. The system is slowing down. And you want to make sure that the read stage is evenly distributed around the cluster, right? If you have read stages that are heavier in one than the other, that means that there's a data skew. So even if you perfectly spread traffic around the cluster, if your data model has an issue, you may still get more reads from one node versus the other. Request response. This is what is talking between the different nodes on behalf of you, the client. Right? You, the client, talks to one node. That node happens to be your coordinator for that transaction. But then everything else is being communicated internally using request response stage. And then finally, validation executor. This is important for keeping things consistent across the cluster. It really doesn't need to happen all the time, but every now and then we need to validate the schema across the cluster. And then finally, what is dropped? Dropped means that of this, there's a subset of tasks that get dropped for whatever reason. So mutation. A dropped mutation means that we were trying to change data and there was a timeout and it told the client that I couldn't take your data. Sorry, I'm busy. At the same time, it may send a message, a hinted handoff message to another node to say, hey, store this somewhere. Or on behalf of the server that's down, store this somewhere. And hopefully that will get replayed. The counter mutation is a type of mutation, but it's a different, but still it's a drop mutation, same thing. Read repair happens when we are reading data, and at the same time, what is repair? Repair is fixing data. So while reading, it's doing a mutation on something else to fix something. Read drops. Read means that it's gotten so busy. It's like I can't even give you data. I'm sorry. Range slice related to read stage, page ranges. It all comes down to the read stage because we're talking about ranges of data in Cassandra. And then request response. This means that there's some issue between the different nodes. There's some issue between the different nodes. Okay. So this was a lot to digest. I understand that. But it's okay. If you're going to continue working with Cassandra, eventually you'll understand this grid, what's happening. I may at some point, when I find this guy named Free Time, I may ask that guy Free Time to help me diagram this to show what's the flow of all of these stages, right? What is a potential flow of all these stages? But I recommend you, if you're working in distributed systems, if you're working on cloud software, I recommend understanding how this is working. You don't even have to look at the code, okay? Just understand this idea of having different stages and having messages being passed around between nodes. Because ultimately, every distributed system that I've seen at scale becomes like this. You have different microservices moving messages around, okay? And just like Cassandra, being a distributed system, you need to monitor it. You then need to be monitoring your different processors or microservices to see how many messages do I have active, pending, or completed, or blocked. So I've mentioned it before, and I'll mention it again. Cassandra is a fairly simple system to understand. If you watch the last session, which is on the read-write, and then if you watch this, and there may be another one that I do on this general, just a re-explanation of Cassandra architecture. In 2 to 3 hours, if I can explain to you how Cassandra works without reading, the code, that means it's a roughly probably an easier database to understand than, let's say, SQL Server. And I know SQL Server really, really well. You think this is complicated. SQL Server probably has like, I don't know, 40 or maybe it has, I'm guessing, but the last time I checked, there were so many different stages for locking and whatnot that it kind of blew my mind. So I encourage everybody that, you got to be an expert in Cassandra, learn about the thread pools, monitor, and by the way, you don't have to be reading code to learn about the thread pools. You just, maybe collect the statistics using tpstats and just see on 10 machines that are on a cluster, like what's happening, But it's better if you use a tool like Prometheus and Grafana or Op Center, because as you can see, 20 times 4, my correction here, dropped is a different type of statistic, okay? That's still 80 times the number of nodes. So 10 nodes, you have 800 metrics, times, even if you took it 1 hour a day, right, for 24 hours. Talking like, 1,600, 1,800, 16,000 or 18,000 metrics. So you have to eventually visualize this information to make sense of it. All right. And with that, I'm out of breath. Kind of exhausted this particular topic. Any questions either on this topic or anything else?
Just one. Sorry. Carry on. Ryan?
Yeah, go ahead.
Ryan, please carry on.
No, go ahead.
Rahul, it is my query is with respect to commit logs. Okay. What I understand is commit when we do the write operation, it first writes to commit log and mem tables, right?
Yeah.
Now the question is, when it writes the commit log, is it writes into one particular node, or try to write into all the nodes, or how it is?
Yeah, good, very, very good question. It writes to every place that data belongs. So the replica, right? If there's replication factor of 3, then it writes to 3 places.
Right into two places. Okay. Okay. Yeah. Okay.
Got it?
Yeah.
All right. Any other questions?
Yeah, if you, sorry, I joined late, so if you already explained it, you can just skip it. But can you expand a little bit on just conceptually what a stage is, read stage versus whatever stage versus, like an executor or calculator, just all those, the classes that end with stage. What is a stage? It's not like Sandra's doing one stage at a time, right? So what is a stage?
Yeah, sure. I mean, it's just it's a thread, and it may have more resources or less resources. But a stage is a difference. So there's something called the flush. Like this is an older one. Let me go to a newer one. There we go. Right. Stage, executor. Stage, executor, archiver. Stage, writer. Recurring memory, calculator. Flush, executor, stage. So you're asking why stage? Why is it called stage? Okay, because it's part of a multi-step process. That's why it's a stage. Versus this is complete in itself. That's it. It's still processing something, but it's processing something in a step-by-step. It's like when you do a request for information, right? It has to go through different stages on different machines before it gives you the data back. Does that make sense?
Got it. Okay.
I mean, I think that's it. Really, I don't see any other. Yeah. And if you look at the definition of SETA, staged event distributed architecture, right? That's what it means. It's you can hear. I'll actually put this in the notes so that when the blog post comes out, it'll be there as well. Okay. It's just a way to move events through the different stages to basically complete something.
Okay, so all the other ones, executor and so on, they run their one thing and they're done. Like it's not like they're part. Okay.
Yeah, that's really what it is. And there's a difference between, let's say, event-driven architecture and stage-event-driven architecture. And that's the difference in like locking, unlocking what's happening. Is just saying, okay, we're gonna have these stages. Active, pending, right? Those are the stages, and it's the different, like for the thing to go through completely, it has to go through all of these different stages before it's done. Maybe I'll write up, specifically, I guess with Cassandra. This explanation talks a little bit about it, right? You have a client request, read stage. So this is node 1, node 2, node 1, node 1. So it goes through all of this stuff just to service that one request.
Got it. Okay, cool. Thanks.
Okay. All right. Any other questions? All right. Well, I will give you all back 3 minutes of your time. We're glad you guys showed up. Recommend getting onto the Meetup group, subscribing to the channel, and see. Yeah, subscribing to the channel. Cassandra Lunch, signing up on the mailing list, just to be notified of new content as well as new events coming up. But this is a meetup that we do every Wednesday at noon Eastern, 11 Central, and we're going to continue doing it beyond COVID. So maybe I'll go ahead and actually just call this out. We don't need to call it COVID edition anymore. Right? This is just Cassandra Lunch now. Okay. All right, everybody. Have a wonderful rest of the day. See you guys next week. Bye.
Thank you.